SuperTest is a test and validation suite for C and C++. Of course, it has got very good conformance with the language specification, but it's also got some special features. One of them is the ABI Tester, which takes care of verifying the calling conventions between compilers or within the compiler. It's got parallel testing that makes it possible to speed up the testing in a nice way and use all the processors in your suite. And there's the depth suite, and that tests and validates the arithmetic model of the compiler and the processor. Okay, I'm going to tell you a little bit more about compiler testing, validation. SuperTest, that's our product. My name is Marcel Weemster. I'm here together with Marjan Damstra. Together we are SolidSands. Let me tell you a bit more about SuperTest. Is obviously it's a validation suite. Owen has explained to you about some of the properties validation suites should have. I'm going to talk a little bit about one specific unique feature of SuperTest that the other test suites don't have. These are three unique features in SuperTest. The first one is that we have a so-called ABI Tester. It's a test generator included in SuperTest. So it's not a fixed suite. You can control what kind of things it generates. And it's aimed to generate the function calling specification. Function calling specification is important, of course, within the compiler, so that one function is called from somewhere and they talk nicely together. But you also have to link to library code, and library code may be compiled by a different compiler. And, if you have those two compilers, you can verify that they actually can talk to each other using the ABI specification. Second feature is that we very simply support parallel testing. Every computer, every laptop has multiple threads inside it. It's very trivial to use that in the testing setup, as long, of course, as you have enough target platforms to run on. And typically, TI, for example, do that on simulators, so you should have multiple of those running as well. It's also very easy to steal cycles from other workstations in the same network. You can configure it so that your colleagues were losing their workstations because there's testing running on their machines. That's very easy in SuperTest. It makes it easy to compress the testing time from many hours to a couple of minutes even. The third one, and that's what I talked about now in particular, is the depth suite. The depth suite is aimed at testing of the arithmetic properties of the compiler, the arithmetic expressions in the compiler. And to understand why that's important, in particular for C and C++, let's take a little bit of a look at these languages, C and C++, why they are still so relevant in the industry today. Everybody will probably agree that C and C++ are not the nicest languages to program in, not the safest languages to program in, but they're hugely popular still. And this is a graph collected by TO. It's a Dutch company who started doing this in 2002. And well, the tracking here, this is the top 10 of what they find are the popular programming languages. They keep track of hundreds, many more than in the top 10. But you can see that C is the number 2 language here for a long time. The top bar, the top line is Java. Java lost its lead for a short time here, but it's now regaining here because probably because of the Android platform. Android apps are often written in Java. But C is still going strong here and will go strong for a long time. C++, by the way, is the green line. It used to be more popular in the early 2000s. It's now going away a little bit, but it's making a comeback here. It's now back at number 3, again, probably because of the Android platform. So that makes C, C++ still very relevant today. And yeah, you may ask, why is that? Because, as we have seen, they're not always the nicest languages. Well, C is popular, and that's my opinion, but I think there's some truth in that, because it provides a very good performance, very little overhead. When you're programming your battery powered device, a factor 2 in performance improvement means a factor 2 in battery lifetime, and that is very, very important and has a very big economic value to keep the time low there. The other thing that is actually related to that is that C is a language that's quite portable between target architectures. If you design a strange processor with strange capabilities, you wouldn't try to run Java on it for many reasons, because it may not have sufficient capabilities to run Java. But always, it's almost always the case that you can port some version of C onto that target architecture. And that's not always safe and not always nice, but it's better than programming that thing in assembly. So what you get is that there are many different implementations of C, actually. And one of the reasons that C can be portable is that the language specification, and I brought a couple of artifacts here. This is my first artifact here. The C++ standard, it's a very big, hefty document here. The C standard is not as big as this one, mainly because the libraries of C++ are huge. Okay, hefty as this document is, C and C++ both allow quite a lot of leeway in the implementation. There's quite a lot of gaps in the specification. And that's particularly true for the arithmetic part. So that's why we get back to the depth suite that I'm going to talk about, and that is the data model of the data types. In Java, you have these arithmetic types over here. Characters may not be an arithmetic type, but basic data types, and there are strictly defined sizes of these data types. Whatever Java implementation you run on, you can rely on the fact that an integer is 32 bits. In C, that's not the case. In C, the C specification says, well, a short has to have at least 16 bits, an integer has to have at least 16 bits, but it may also have 18 bits, and it may also have 32 bits, or 48 bits. And actually, implementations do that. Implementations make use of this flexibility in the language specification in order to map efficiently to their target architecture. Sometimes some compilers allow you to change the data model really on the fly with compiler options, and that has huge impact on what the program does. Now this implies that the arithmetic that you're doing on the target architecture, on the program, doesn't always do the same. And I've got a couple of examples here. We have here examples where we have the choice of the size of the integer. We may use 16-bit integers, 24-bit integers, 32-bit integers. If you would do a simple computation like 200 times 300, doesn't fit, the result of that doesn't fit in 16 bits, so you get an undefined value in C on a 16-bit processor. On a 24-bit processor, you get something valid, like a 32-bit processor. If you make the computation a bit bigger, it wouldn't fit anymore on a 24-bit processor, but still would be alright on this 32-bit machine. Now, if you go into unsigned arithmetic, that's arithmetic without negative numbers, then actually all of these sums have a defined value. So if you go to the biggest here, 5,000 unsigned times 5,000 unsigned, on a 16-bit architecture has to have this specific value. 24-bit architecture has to be this specific value. And for a 32-bit machine, you actually get something that you would recognize. But these values here, they are actually according to the language specification. Now that is a bit of a problem, of course, for a validation suite, because you cannot put into a validation suite this multiplication here and then compare it to a specific value over here, because that value depends on what your data model is, what the data model looks like. So in order to do that, we have in SuperTest the depth suite. The depth suite is huge. I've got here, all of these lines are different data models. So just to explain a little bit what's going on here, we have an 8-bit character, 16-bit shorts, 32-bit integers, longs, and that's it, and 32-bit floats, 64-bit doubles. Well, all of these are different combinations of data models. And the two well-known data models, the typical 32 and 64-bit data model that you find in your typical smartphone, your laptop, your iPad, etc. They are these two data models over here. They are very often used, of course, and they're quite common for most platforms. But when you take a look at an average car and take a look at all the processors in there, you find many, many more strange processors in there with strange data models. And you find 8-bit processors, 32-bit processors, 16-bit processors, 16-bit processors with very weird division arithmetic, which is allowed in C as well. You find 24-bit processors, very popular in audio applications. All of these different data models, for each of these different data models in SuperTest, we have a depth suite. And we didn't make up these data models. These are actually requested by our customers who ask, okay, our compiler target looks like this. Can you generate a test suite, depth test suite for that specific data model? And so we have accumulated more than 30 of these. Can you actually check the results of the depth suite generator?
Yeah.
The answer to that is yes, but it requires quite a complicated compiler setup by an emulator compiler that actually tests all of these different platforms itself. So this is what's included in SuperTest as well. It's one of our unique features, really arithmetic testing for the specific data model of the target architecture. Each of these lines represents more than 2 million test cases, not one test per program, because otherwise it would take too long to run, but they're condensed a little bit into groups. But more than 2 million test cases for each of them. So that's what I wanted to explain about the depth suite.
When you, if a test, you've got these 2.3 million tests, if an individual test fails, how do you then ensure that it does not prejudice the integrity of succeeding tests?
They're grouped by about 100 per one test program. And each test is really an independent piece of code with its own variable usage, its own instantiation of the variables, doing computation and doing the test of that. What you do as a developer when you're confronted with a failed test, it will actually point out, if you have the debugging on, it will point out, okay, this was test number 67 that failed. You can then take just that code for 67 out of it, put it into its own program and check that that also fails. So the isolation of the error itself is not a huge issue as far as I know from the experience we had and the feedback we have.
Just, I mean, looking at this from the perspective of a user, putting these together, I mean, is there a facility in there for the compiler to actually just generate warnings on some of those rather more audible cases where it's overflowed? Because I understand it's defined in the language standard, but it's one of those things where you kind of hope that any coding standard worth its metal would say, don't do this.
Yeah, true, but when you have a function that takes two arbitrary arguments and in there you do some unsigned arithmetic, you really don't know what values these arguments have. And without the knowledge of the values, you don't know whether the overflow is happening or not. And you have to make sure that it's going to be what the language standard has. Usually it matches, of course, with the implementation of the target architecture arithmetic. So it's not very costly yet. But you are also right that it may not actually be something that the programmer wanted to happen there. But that's very hard. You need value propagation in your static analysis tool, and that has limits. It doesn't look through everything. So failures is from today, I think, the official distributor for SuperTest in the UK. Thank you, Chris.